Yeah, let's start.
So, good evening, folks. So, welcome you all back into the demo session. And direct apologies for delaying the session due to some network issue from my end. So, let's get started. So, this is more of like a demonstration session wherein we will guide you through, what will be taught in this course and what can you expect from this course and what are the outcomes of this course. So we'll have a brief overview of that, and once that is done, Mr. Shivam will guide you through the AI aspect of the CFD development, and once that is done, we will jump into the coding aspect, okay, wherein we'll see how to code up the problem, right? So CFD, as you know, it's basically a way to convert your partial differential equations into computer codes, so that when you solve them, you get an understanding of the governing dynamics behind the equation, and you get a feel for the solution as well. Okay, so the fluid dynamics, as you know, it is all about the study of flow patterns and sort of interactions and etc. So in this course, we will be focusing exclusively on the numerical aspect of this course, that is, writing own solvers for standard cases. And once that is done, you should be able to go ahead and write up your own codes. Okay. So basically, when you look at CFD, you can basically divide that into three steps. So one is pre-processing, another is solving, another is post-processing. Any problem can be divided into these three steps. Okay. So in pre-processing, what we do is simply we clean the geometry. When I say clean geometry, it typically means, let's say, you have a nozzle, 3D nozzle, okay, or let's say a 3D pipe. This pipe is axisymmetric, right? So if you can carry out a 2D simulation of this and apply the axisymmetric boundary condition, you would be getting the solution of the problem. Okay, so that's what when I say cleaning geometry means. Okay, so we'll try to negate all the unwanted parts of the geometry, like nuts, bolts, so that it doesn't affect the computational time for us, because strictly speaking, we are only interested in the fluid interaction. That's what we're focused on. So we'll clean the geometry, and we'll also mesh the geometry. Once the geometry is meshed, we'll mesh the geometry. So meshing is actually, basically you have the entire geometry, you divide them into finite volumes. Okay. So when I say finite volumes, so typically, right, discretization, right? So what is typically discretization is? So you have a PD, and if you convert that into an algebraic equation, so that is called as a discretization. Okay. So let's take a simple equation. Let's say dou u by dou t plus u dot del u is equal to 0. Okay. Now I can write this as I can write this simply by using Taylor series. As we look into that, what Taylor series is. Okay. I can write this as ui at n plus 1 minus ui by delta t and plus so on. Okay. So this is what is typically referred as discretization. That is, we can't directly solve that partial differential equation. Computer doesn't even know what a partial differential equation is, right? So we have to set it up into a means by which the computer can understand. Okay, and that form of setting up is called as typically discretization. Okay, right? So meshing is actually a form of discretization, wherein which you divide the entire domain into finite volumes so that you can apply these equations at each and every volume. Okay, so you have typically three forms of discretization. So one is the finite difference, other is the finite element, and this is the finite volume. Okay. So in this course, we will look into finite difference first. Once that is done, we'll deal with finite volume, and we'll also use ANSYS, which is a finite volume tool. And finite element, is mostly used for structural problems, but it is not restricted only to structures. You can also use it for fluid flow applications as well. Okay. but they are rarely used. Okay, fine. Okay, in finite difference, this is what happens. Okay, so we have an equation we discretize using algebraic means by applying the Taylor series approximation, and we have convert those equations into an algebraic form. Okay, and in finite volume, we integrate the differential form of the equation. Okay, so we have the Navier-Stokes equation, right? So dou u by dou t plus del dot dou u is equal to minus dou p by dou x plus the viscous term over the right side, right? So we integrate that equation directly, and we will convert those terms into source term and non-source terms, and then we'll try to solve them. Okay, so that is what is typically called as a finite volume. Okay, so that is what happens in pre-processing. So we clean the geometry and mesh it. In solving, we set up the boundary conditions, which is the most important aspect of a CFD problem. If you set up ill boundary conditions, you will get incorrect results. Okay, when I say boundary conditions, it typically means what is the inlet pressure, outlet pressure. Are you following a Dirichlet condition or a von Neumann condition and so on. Okay, so we'll look into that as well in this course. And following that, we will do post processing, wherein which once we solve, we'll get a set of results. We'll try to analyze them using CFD post and ANSYS. Okay, and which will post process by applying visualization tools to see whether we can observe temperature contours or the velocity contours or the boundary layer, the velocity contours is the boundary layer, or the airflow over the body, something like that. Okay, so that's what we'll be looking at in the post
Yeah,
processing.
we also have initial conditions, right, in the solving part, because if
Yes,
the problem is an
yes.
unsteady,
So,
yeah, right?
yeah,
We have
yeah.
initial conditions.
When I typically mention the boundary condition, it includes under the number of boundary condition. It also typically incorporates the initial condition as well. Okay, so you, broadly speaking, you can divide the problem into a steady and a transient base. So in steady base problems, you don't have to worry about the time stepping and all sort of things. Whereas in a transient problem, you have to worry about the time step size and all sort of things. Okay, so fret not. Now we will be looking that in detail. Okay, about all sort of things. And this is what is the entirety of CFD. Okay, this is in a simple nutshell. Okay, right. So hope that is clear to everyone. Right. Moving on. So today we'll start with the one-dimensional linear convection equation. You might ask why. Generally, when you start linear algebra, you start with matrices and then you go on to eigenvalues and so on, so right. So your CFD also needs a basic equation, which is the one-dimensional linear convection equation. Okay, where when I say linear, it typically means that the dou u by dou x term is a term attached to the dou u by dou x is a linear term. Okay, that constant c. Okay, it's a constant, right? So this is the equation that we'll be looking at, and we'll try to see how to solve this. Okay, where c is our wave propagation speed. Okay, and like I said, we'll set this up. We'll set up this equation in our computer, and then we'll try to solve it, and we'll try to see what happens. Okay, right? So this is our fundamental equation. Now, when we typically say that we solve an equation, what do you exactly mean by that? Is so the Taylor series approximation, right? Let's say if I have a function x plus del x, I can write this as fx plus f prime x plus square by 2 factorial f double prime x and plus so on, so right. I can go till higher order terms as well, right? Okay. So this is what is referred to as the Taylor series expansion, right? Okay. Now if I were to apply this, we have let's look at that equation. So I have dou u by dou t plus c dou u by dou x, that is equal to 0. So I can so here you have two variables, time and spatial. Okay, so we can discretize this as, watch carefully. First, I can write this as let's say generally u of, let's say, x plus del x. Okay, I can write this as u of x plus del x u prime x, where u prime x typically means the dou u by dou x. Okay, plus del x square by 2. I can write this as u prime of x. So you don't get confused. U double prime of x plus so on. So okay. Now let's try to subtract this equation, this whole equation. Let me bracket this again, in case you're looking at with u of x. Okay, you subtract that, so you will have u of x plus del x minus u of x. Okay, and if you divide it by delta x, okay, what will happen is you will have all these terms on the right hand side remain. Okay, so I'll have simply u dash of x plus delta x by 2 u double dash of x and so on. So okay, right, so we have a derivative in here, okay, u dash of x. Okay, so this form of approximation of a derivative in terms of the algebraic means is called as a discretization. That's what I said earlier, right? Okay, so we can write the equation in this fashion as well. That is the u dash of x, which is simply dou u by dou x, can be written in this fashion. Okay, hope this makes sense to everyone, right? Matishwar, any doubts? Parul? Okay, so moving on. If you have some doubts, please do put it in the chat box. Okay. Right. So now let's focus on this equation. Okay. I can write this dou u by dou t as ui n plus 1 minus ui at n by delta t. Okay. So the del x, the d, del t, computer doesn't understand those terms, right? So what we'll have is, so we have, how do you solve this equation simply? So we have a domain, okay? So let's consider this as our one-dimensional domain. And let's say this is bounded by some limit, okay, 0 to L. And we divide this domain into, let's say, some n number of grid points. Okay. So we divide this domain into, let's say, n number of grid points, okay? Each one is called as a grid point actually. And we apply this equation at each and every point. So we assign this each point an index I, okay? So this is for looping through the each and every point, okay? And the variable which is u, okay, at that point is represented as u of I, okay? And this is at a time level, let's say time level t is equal to 0. So when I move into a new time level, let's say time t is equal to 1, let's assume for a second, again consider the same thing, 0 to L again. Let's consider the division of the nodes, okay? So at these grid points, your UI will now vary, okay? Because you are integrating the solution, okay? Basically, you are solving the equation. So here you will have a new UI value, okay? So basically, as you go through the different time steps, when I say time step, it means the dou u by dou t term. Over a period of time, you solve the equation at each of these grid points, you will get a solution, okay? So that's what is we represent it as a time level n plus 1, okay? So this is a time level 0, time level 1, and it goes till n. N is what we defined it, okay? Okay, right. So I can write this dou u by dou t as ui n plus 1 minus ui n by delta t. So this form of writing is called as a forward differencing operation. And for du by dx, I can write this as ui n minus ui n minus 1, which is nothing but our backward difference. Okay. So once I discretize this and then write it into this form, which is the dou u by dou t, I will have an equation which is like this. So, and if I, because ui at n is known, because once we initialize, so when we say solving, that initialize the variable, so we'll initialize, so we'll know the value of ui at each and every point at t is equal to 0. But none of the values of u at t is equal to 1 are known, okay? So we'll have to use somehow these values, okay? And that's so that these values will get converted into a new time level, okay? So this is how solving happens, okay? And the t is equal to 1 will translate the value to t is equal to 2 and so on, so okay? So this is how the solving happens typically, okay? Now ui n plus 1 is unknown, which is the value of u at the new time step. So we can write this as ui n minus c del t by del x times this whole thing, okay? We just cross multiply the terms. And this term has a special significance in CFD. We'll come back to this. Okay, just remember this term for now. This is called as a CFL number or the Quran number, right? So this term actually dictates whether your solution is stable or not unstable, right? Okay. Fine. So now, once having obtained this term, okay, we'll have to set this up in our code. So we'll be using certain libraries like NumPy, MATLAB, Matplotlib, so, and we will restrict ourselves to a domain where x is from 0 to 2, and we'll divide the domain into 61 points. Okay, and we'll consider 20 time steps with a time steps size of 0.025. Okay, so this is just an approximation. You can consider whatever you want. Okay, right, and we'll solve this equation. Right. So when I say division, basically what does computer understand from that is, so we have a domain like this. Okay, so we have from 0 to 2. Like I said, you have like the values of u at these nodes are known. Okay, this is just for illustration. Okay, so I have ui and ui plus 1, where I plus 1 typically means the next index, I minus 1 typically means the previous index. Okay, so because we have the x plus delta x in our Taylor series and x minus delta x, right? So these terms are typically written as I plus 1 and I minus 1. Okay, hope that makes sense. So we'll divide this into n number of nodes, and we'll apply the formula at each and every so as to get a hang of it. Okay, right. Is it clear, guys? Any doubts so far? So moving on. So again, so let me just put this into your mind. So you solve these equations at these nodes. Okay, so you have the ui n plus 1, right? So if I rewrite that equation, ui n plus 1, that is equal to ui n minus c delta t by delta x ui at n minus ui minus 1 at n. Okay. So let's say I operate in here, right? So ui minus 1 typically be the value of u at this index 0.5, and ui at n is typically the value of u at this value of index x. Okay. So this is what is typically. So you have to use some sort of an array or a vector, so as to get values of these, so as to store the values of these variables. Okay. Fine. And once that is done, you can solve the equation, and that we'll do at the end of the session. Okay? Close to the end of the session, right? Okay.
Yeah, just wanted to add one thing. Go to slide number 8.
Slide number 8. Okay.
Yeah,
Yeah.
yeah. So yeah,
Sanjay, I think your voice is a bit breaking. Sanjay? Okay. Once he joins, we'll continue. Okay, fine. Right. So what I was saying is, so focus on this thing. Okay. So we'll solve the equation, and we'll get the values of these indexes, value of the variable at these indexes. Okay. Right. So let's look at the significance of that equation. So convection typically means, right? So what is typically convection? Is basically flow. So whenever something flows from one end to another, we call that as convection in fluid flow terms. Okay. Now this term which I was saying is C, which is the convection speed. This actually dictates the stability of the solution. Okay. If I change the C to some other value, your solution might blow up. Okay. And couple that with the delta T by delta X term, which I was saying, and this is called as a CFL number. It's one of the hallmark numbers in fluid dynamics solving. Okay, because if you set this number very high, your solution will blow up. If you set it very slow, it means you will take much longer time for the solution to converge. Okay, we'll look into that. You don't worry about it. Okay? And when we have a positive value of C, it typically means that the wave will move right, and when you have a negative value of C, it means the wave moves to the left side. So, and its applications are in the fluid flow and the traffic flow problems. Okay. So moving on. So this is what I said earlier. Okay. So we have the Quran number, and the Quran number has to be less than 1 for stability, so that the stability analysis will be covered by Sanjay in the sessions, forthcoming sessions. Okay. Now the simplification that we do here is we didn't consider non-linear term. Okay, that u dou u by dou x and the right hand side of the Navier-Stokes equation. This isn't also considered in here, right? Okay. So when we consider it, then we have to use the appropriate schemes properly. Okay. So we look into Wax-Lindorff schemes and other stuff. Okay. So now we have to solve the equation, right? So I have the equation in this form. Value of u at a new time step is nothing but value of u at a current time step minus c delta t by delta x times ui at n minus ui minus 1 at n. Okay. So we are solving this equation now, right? Okay. Now we need the condition. So what sort of condition are we going to do is we'll assume a step function u value of velocity like this. That is u is equal to 1 at this level and u is equal to 2 at this level. So we'll have x is equal to 0 to 2. X is from 0 to 2 here. So between 0.5 to 1, we'll assume value of u as 2, and rest other in the rest of the domain we'll assume the value of u as 1. Okay. So this is our condition that we are going to give, and we'll make sure that the computer understands it, and we are able to solve this equation. Okay. So let's look at a bit into the Taylor series notation. So when I said the forward differencing and the backward differencing, it all depends on what sort of value you want to obtain. Okay? So if it is u of x plus delta x, so you are moving ahead of you are moving into the next node. So and you want to obtain the value at the next node, you have to use the value of the current node. Okay? So that sort of differencing is called as a forward differencing. So we have, let's say, I have a domain like this. Let's say I have I plus 1 and I minus 1. Let's say if I want to get this is x minus delta x, x plus delta x. Okay? Where delta x is the difference between the any two nodes. Okay, so we'll consider same delta x between each and every node. So this form of discretization is called as the structured grid approach. So recall what we wrote earlier. So we have u of x plus del x. I can write this as u of x plus delta x dou u by dou x plus delta x square by 2 factorial dou square u by dou x square plus higher order terms. And I can also write u of x minus del x as u of x minus del x dou u by dou x plus del x square by 2 dou 2u by dou x2 plus higher order terms. Okay. So this sort of writing is called as a forward differencing idea because we are moving forward into the next node, and this one is called as the backward differencing because we are writing into the back of the node. Okay, that is the value at this node is taken from the previous node. Is called the backward differencing. Okay, and if I were to convert this, like I said, if you let's mark this as equation number 1 and this as equation number 2. If I subtract 1 with u of x and divide it by delta x, okay, so I'll simply have, try to replace this one with u of x plus delta x. I'll simply have what? I'll have dou u by dou x plus the higher order terms, okay, order of, let's say, delta x. Because when you divide the whole equation by delta x in this one, the first higher term will be a delta x. Okay, so that's why this is a first order approximating scheme. Okay, Let's do the same thing with 2. Instead, we'll subtract u of x with u of x minus del x. And if we divide it by del x, we will also get the same thing as dou u by dou x. And this is also an order of del x scheme. But notice the difference in here. You have a u of x plus del x minus ux, and you have ux minus u del x minus del x. So even a simple choice of this scheme will result in varying solutions. Okay, and in our problem we use this backward differencing scheme, u of x minus u of x minus del x. Okay, so I leave that reasoning to you. Okay, you have to think about why we went with our backward differencing thing, not the forward differencing. Okay, right. So that's what is discussed in here. So when you have in the accuracy of differencing, so we have one is what is called as the forward differencing, u of x plus del x, and the backward differencing, and you know what Taylor series is all about, right? Okay. And we also have something called as the central differencing scheme, wherein the value at a node, so again consider the same thing, I minus 1. The value at a node is influenced by the neighboring two values. Okay, this value as well as this value. So because it takes one more value, so this is actually a second order stable scheme. Okay, so we had that u of x plus del x, right? And if I subtract u of x minus del x and divide it by del x, I will have the same dou u by dou x, but this time it will be order of delta x square. So this is a second order approximating scheme. That is the leading order of the derivative, so delta x squared. Okay. Hope this is hope everyone understood this, right? Abhi Patel, Harsheen, any doubts? That is when you substitute the u of x plus del x into this and u of x minus del x, you have the dou u by dou x and the order of delta x squared term. So this is what is shown in here as well, right? Yeah, as you can see, order of delta x squared. Okay. So you have the u of x plus del x minus u of x minus del x. When you subtract them, you will have terms like this. And when you get the dou u by dou x, you are left with this term. And as you can see, the highest term on this term, on the higher order term, is delta x squared. Whereas if you look at the forward and backward differencing, okay, forward and backward both have a delta x. So which means the central differencing scheme is actually much more stable than the forward or the backward differencing scheme. So this is what is the funda for today's session. Right? And while again, like I said,
Yeah. Also, guys, the dou u by dou x is what is the exact solution that we have, and the approximated one on which you apply a certain scheme, that is solution. So the difference of that is what is the order of accuracy of that particular scheme.
yes, yeah. So this term is actually the approximation, and the rest of the term is called as the truncation error. Okay, so if you add the truncation error to this approximation, so let me write this. So this is what is called as the approximation, and this is the truncation error term. If you club both of them together, you will get the accurate value of dou u by dou x. But because the delta x is so small that you can ignore this error, so this is what we refer to as approximation. Right. So moving on. Now we'll look into how AI-based applications can be, incorporated into our CFD analysis. So Mr. Shivam will take over from here. Okay, I'll just, into the PDF. Just give me a minute.
Praveen, I can present actually.
Yeah, so there is a doubt that what is the zero? So that zero is nothing but it represents the order of accuracy. When you
Yeah, it's
write
O.
that
It's not Q.
O of,
O.
yeah, it's O, not zero, it's O. When you write O of delta x, it means first order accurate. Delta x power n is nth order accurate.
It's not 0, it's O. Okay.
Hello?
I don't know. We'll derive all of these things. Okay, right? We'll have a separate session. Me and Sanjay will derive all of them. So over to you, Shiva.
Am I audible to you?
Your voice is a bit low.
You can make me the presenter actually. Hello?
Presenter, I think Dinesh are allowed to do that.
Because I am also having things to write. So that's why.
Yeah, Shivam, you are present or no? Yeah, hello, Shivam.
Yes, sir, I am present in just a second.
Yeah, yeah.
Hello, sir.
Yes, Shivam.
Not getting that presentation.
Yeah, still your voice is very low.
I'm not getting the presentation button here.
You are present, right?
But I'm not getting that presentation button here.
One moment. Just a
I'm not
moment.
getting that option to share my screen actually.
Okay, just a moment. Yeah, now you are in
You have
iPad,
to
right?
yes, sir, I said.
Yeah, you need to upload. There is a
Upload.
plus sign. Yeah,
Yes, sir.
plus sign. That please upload your presentation. You have created in PDF, right?
PDF is also there and PPT is
Yeah,
also
yeah.
there. So,
Yeah, please upload PDF of
a
presentation.
PDF.
Click on,
Okay, sir.
yeah,
Yes,
click
sir.
on plus and manage presentation.
Sir.
Yeah, sure. It's
Yes, sir,
uploading.
I've uploaded. Yes, it's uploading.
Okay.
And once this is done, sir, you can give access to SPL,
Yeah, yeah. I will.
code. Okay.
So hello everyone. Am I audible to everyone? Sir, can you confirm one?
Yeah, yes, you are
Yes,
audible.
sure.
So everyone, till now we saw how Praveen has solved the 1D wave equation and which was linear in nature. Now, what if I ask you all, what if the equation is non-linear in nature, right? So if the equation is non-linear, suppose we have a full Navier-Stokes equation, and then again we have to solve some really complicated industrial problem, right? So I'm going to talk more about the applications, like the course name itself is Fundamentals of CFD and its application. So like Praveen has talked about the fundamentals, which is understanding how these equations come into play, and then the applications part. So as I was talking, if what if the geometry itself is a complex one, right? So then we are not going to write code for that, right? So today, first of all, I will talk about how this first part which was majorly about the code, and the second part which will be the application. So first question I will ask you is, so my first question to all of you is why CFD is used as a tool for the design process. Right? So we know like the design process for any of the application. Let's say we want to design a wind turbine, right? I will take just few common examples. Like most of you will be here from aerospace background and mechanical background, I assume. So what will be the design process, right? So anyone who can answer in chat box.
Shivam, can you be little louder also?
Sure. So anyone can tell me about the design process for a wind turbine blade. So is this much voice is correct? Or
Yeah,
can I
now it's
still?
fine.
So anyone can answer in the chat box. That's great to listen your views also. I see multiple users are typing. So I'm asking, like, if there is a design process for wind turbine blade, how will we be doing it with the help of CFD or any other process, not CFD for that matter? Right? Okay, Akhil, to reduce drag, CFD is used. That is a very particular aspect of CFD. CFD is much more wider than just lift and drag, right? But I don't know the design process for wind turbine blade. Okay, so I will move ahead. Uh, So here first I will explain some of the things in this slide. So suppose we have to design a turbine blade. Here in the picture I have shown you, right? This is a turbine blade. So now suppose you guys must know aerofoils, right? So there are around thousands of aerofoils. So what if airfoils will be considered initially? Yes, NACA airfoils. I was coming to that only. So suppose you have thousands of airfoils. Now, how will you choose out the airfoils from those thousand ones, right? So that will be, suppose for example, I have to make a blade out of only one aerofoil, right? So you will be seeing the lift and drag coefficient, and from that you will get the torque coefficient in a wind turbine blade. So there will be thousands of such aerofoils and there will be thousands of such combinations. Not even thousands and millions, there will be the combinations, right? So suppose we have a zero knowledge of how to make an efficient blade. I'm saying that, and my knowledge is only for the aerofoils. Right? So how do we design a blade which actually works? First of all, this is the question. And then we also want it to work, but also to be very efficient with converting the free stream wind into the mechanical energy, right? So now traditionally what would have happened, I will say, so traditionally what will happen, like people will design turbine blades, right? And then they will test it on wind farms, right? So, and then they will take the data and see whether the design they made is good enough or not. But now if you imagine about this, okay, I will show it in the slide. So this traditional process, this is a flow chart here I made. So like you will make a prototype of the blade, okay, with the aerofoil type, and then test it on the field. Now there are high chances, even if you do the probability of this uh, experiment, there are high chances that your wind turbine blade will be not efficient or it will not work also. So then you again modify the prototype and then repeat the process. Now, if you do this all this experimentally, if I show you on the very right side of your screen that there will be the cost which will be incurring with this, right? That will be the material cost, manufacturing cost, the machinery needed for manufacturing, right? The testing equipment, and then the wind tunnel or a test bed. Like if you are testing on actual field, you will need a test bed. Now all these costs will be actually recurring in nature. So what do I mean by recurring? That for each of the cycle which I have shown in this uh, flow chart, every time you do this cycle, you will have those costs being again and again coming into the picture. Right? And that will lead to, even for designing a small, like a decent blade, not a very efficient one, the cost will go around till 10 to 15 crores. Right? This is actual numbers. Like if you see, there are few companies only which have the wind turbine blades data. So this is a very, even a smaller estimate of what they would have spent on designing a blade. Right? Now I will go ahead and tell how CFD comes into the picture. Right? So now why we are learning CFD is because we want to basically reduce our costs for designing new products. So what do we do in CFD? What do we do? Right? Now we understood like how we can make a code. Suppose our code is working, it is not blowing up. Now what is the next procedure? Right? So, so here on your right side of the screen, right? Process 2 which I have written, CFD process. So here I have shown how a general CFD process works. Like when we learn about the ANSYS Fluent, I will tell you all this in detail, like how a general CFD process for any design thing goes on, right? So first of all, we validate our CFD models. Now, when I said like the experiments, we are not going to do the experiments, and but we will take some of the benchmark experiments, which are said. What do you mean by benchmark? As in the experiment which is made just to validate our CFD solver, right? Whenever we make a CFD code or anything, we validate it with some experimental data. So first we will make a CFD model, right, which will be a code or it can be a commercial tool like ANSYS Fluent, and we set up our things on that, like the discretization scheme you saw earlier, that is first order, second order. There are many more things like that. And then we change the design, right? So now suppose I told you, right, there are thousands of aerofoils and then there will be millions of combinations. Right? Out of this, you will change some of the design combinations, right, and make a blade out of that. And then you will evaluate the performance. Now by performance, what do I mean? Either lift you can see, drag, Okay, and in wind turbine aspect, if I say torque coefficient, okay, these all things we see, or the thrust coefficient, right? And then we finalize the design. So this is a basic layout of what a CFD process is, a very basic layout. Right now, if we see the cost here, which is an important aspect, right? We were doing like CFD was initially made to actually cut out the cost. Uh, so if we see the material cost, manufacturing cost, all those things are here because we are doing one experiment, right? Only one experiment. Now these costs earlier were recurring and now they are non-recurring. See here I have written these costs are non-recurring in nature. That is, you will only spend on them one time and then you are done. Then what will be the recurring cost now? That will be a CFD engineer which you will hire and a high performance computer that you will need to run your CFD simulations on. And now see the cost what I have written, that is around 2 to 5 crores only. Right? So that much reduction in the price with just the help of CFD. So I also want to put your perspective onto a new area, which is right now, because in this course we will discuss a little bit about that, how AI ML, like when we do ANSYS Fluent and tutorials, we will also discuss this part in, we will touch upon this, right? So how AI ML and CFD are being correlated. Nowadays, like it's the day of the data, right? So everything is being clubbed with data. And CFD is one of those fields in which you generate a large amount of data. Right? When people say na like big data and all, so CFD is a domain in which we generate a very large data. Right. So in that sense, if in future classes I will give you some examples from what simulations I have done, and tell you how much data we are generating, right? Large data. So when you have large data, you try to find what patterns in that, right? As a human being, we are inclined towards seeing patterns, right? Anything which human eye finds attractive is actually a pattern. If you guys notice this about yourselves. So anyone here who can tell me about some natural patterns which they have observed, like till now? Natural patterns, as in nature, anything? Anyone in chats? Constellation, good. That is a single pattern, not a recurring one. Like it is just there in the sky. Okay, good. Next, golden ratio. Good. I was expecting this answer actually. Golden ratio. Okay. So coming back to this, I will actually tell you touch very briefly on what AI/ML is doing in the field of fluid dynamics more specifically. So the first question which comes into the mind is how we can reduce the cost further. If I ask so, how can we reduce the cost further? Right. Still, if we see like from 15 crores to we came down to 3 crores. Now, if we further want to reduce our cost, okay. So this is with the help of AI/ML, right? AI/ML clubbed with CFD. Now, talking about the patterns, there are certain algorithms such as the COD or SVD. I will come to their full forms later. Right now, just remember there is some algorithm called as POD or SVD, right? And there is something called as reduced order model. So I will come to each of them one by one. Right? So see on the right side, suppose we have seen this canonical flow. Canonical means the easier flow or a simplified flow, right? So suppose a flow over a flat plate or flow over a cylinder. These are called canonical flows in fluid dynamics. You guys will get accustomed to these all terminologies slowly, right? So when you see this canonical flow, you see that the vortex shedding happens, right? If I here, like this is the vortex, and then this is the vortex. Right? A vortex will be shed from here, and then a vortex will be shed from here. Now this pattern will happen sinusoidally. Right? So if I say see the lift coefficient of this uh, flow over cylinder, or the drag coefficient, you will see the pattern something like this, sinusoidal pattern. Now suppose I have this data, but this data is itself a very big one, like for say 2 TB or 3 TB, or even say so 10 TB of data. I want to read this data to make some model. I will not go there, but what we do is, essentially, if I say, we take this data and we put it into these algorithms which I said, POD, SVD, and then we totally compress this data into, let's say, 10 GB of data, from 10 TB. Now why this is important in today's day and age is because I told you large data sets are being made even from the simulations, like a CFD simulation you guys do. It will make a large data set, but to store them or to keep only important features, keep important features from those data sets is important. Now what are these important features? These are waves in sense of fluid flow. If you see here in this picture, mode 2, you can see these are waves. Like the blue one is a negative magnitude, then red, this area is a positive magnitude, this one is again a negative magnitude, this one is again a positive magnitude. Right? So these are waves. So these waves are important to understand. That much I will say right now. Okay, I will not go more into detail on how these algorithms work or why we are doing this. I told you why we are doing this, like to store the data or to see important features. These are two important points here. And then we make reduced order model out of these. Now reduced order model are something of an advanced concept, and we will touch briefly upon this. Now exciting part which I want you guys to be introduced with is the last one which I will show you. Now in AI/ML generally, what we see is we want to reduce our cost. Now how will that will happen? I will give you an example. Okay, so suppose I have a wind farm, right? Just any one of you who has seen a wind farm in real life? Anyone? Or in which format? Yeah, Sayan, you are right. It's decomposition only. Whatever guys you have read in the matrices and determinants chapter, na, that will be applied here. Something related to eigenvalues and eigenvectors. That much I will say. Group chunks are in which format they are being stored. So they can be stored in any format you like, CSV, XML, VTK, anything. Let's not go there. Let's not go there. Anyone who has seen a wind farm in real life? Anyone here? No one? At least in pictures? Anyone? Yeah. Okay. So when you see a wind farm, it's generally like if I am drawing a top view of that wind farm, okay. So it will be something like one wind turbine is here, another one is here, another one is here, something like this, right? And we guys know from our, you know, satellite data that the wind speed is mostly from this direction, or from in September it is from this direction. So how do we put these turbines here? Right? Because if you think about it, it's just a fluid dynamics problem. Fluid dynamics, or even you can say so it's an aerodynamics problem. Like how do we keep the turbine so that the what we need power output to be the maximum. Power output to be the maximum. So what we do here is, suppose I will show you now in this. Right. So you see this left hand side of your slide. Here I have this box made, right? This is a 6 by 6 box. Assume it as a piece of land. I'm just giving you an example. I will not go in detail. Just giving an example how AIML is being used with CFD. So this is a box with 6 by 6. That means 36 spaces are there. Now, suppose you are an engineering firm and you get a project to place 8 wind turbines in this piece of land. So how are you going to decide where to put the turbines? You can put 6 turbines here, 2 of them here, right? Or you can put 6 turbines here in line and then 2 of them here. Or you can put 6 of them like this and 2 of them like this. Right? And I am telling you that the dominant wind direction is this one, north northeast. Okay, just some initial information. So if you see on the right of your screen, I have written like there are 36 squares available in a 6 by 6 area, right? And you have to keep 8 turbines. Now, if we apply our knowledge of permutations and combinations, right? So here, if we see this formula for combinations, so there are around 9 million combinations in which you can put these turbines into. Right? Now, just imagine the size of what and these every combination you have to run a CFD and then check. Okay. With some common knowledge, you can, of course, every time you can neglect like this one, like placing 6 turbines here in line is definitely not feasible. You know that. But there will be some combinations in which you can't tell just by your common knowledge that this setup is not efficient or it is an efficient one. Okay. So there are 9 million combinations, and for each of them you have to do CFD. Now that will lead to again high cost. So to cut down the cost, we have AIML coming into picture, and there is something called as evolutionary algorithm here. That now I'm introducing the term evolutionary algorithm or genetic algorithms. A genetic algorithm is a part of evolutionary algorithm, okay, which is generally used in design processes. So here the below picture, that one on the left hand side, here I have shown how people have done the studies and shown like if you place a wind turbine in this format, this one, right? So this will give you a most efficient output. Or if the turbine height is low, for example, 50 meters from the ground, and you put it in this format, it will be good. It will be efficient configuration for placing wind turbines in a wind farm like this. So these are all things done with the help of AIML. Okay. You can use this genetic algorithm along with your CFD code to get answers like this. And the last part which I want to touch is how artificial neural networks. Now, I will briefly, in future classes, I will also briefly touch upon what I mean by AI, ML, and then what I mean by deep learning or ANN. Right, that all we will briefly touch upon that. And then here I have written like ANN is used along with the CFD data to again get the trends of the CFD data. Trends as in patterns. So that's all. If you guys have any questions, you can ask me. Otherwise, Praveen, you can put them the code. I hope you guys are clear why we do CFD, why we learn about the commercial softwares which are available, or for that matter, the open source one. And most important, like why do we code about CFD? What is POD and SVD? It is a decomposition, Vishwas. It is a matrix decomposition, and which is used to find out the eigenvalues. And that's it. Having any other doubt? Praveen? Any textbook we should for CFD? Yeah, we'll let you know. Yes. The one by Versteeg and Malasekara is a good one. Dinesh sir?
Yeah. Yes, thank you, Shivam, for giving this beautiful insight of AI/ML in CFD. Yeah. So now we will go to the last part, which is like Python coding. So, Praveen, now you are presenter in your system. Let's start that. So, guys,
Yes.
there are many more things to learn. Okay, the good thing, which first we should understand why we want to learn CFD and what actually CFD. So basically, these are numerical techniques. So which reduce lot of experimental cost. You cannot keep experimenting. So these are simulation techniques, guys. And as you know, the computer power grown, these tools becomes very handy. And now uh, further, this artificial intelligence, which is like basically legacy data basis, results which we can be further used and make even things more quicker, if I am correct, right, Sivam? So
Yes sir, yes sir.
yeah, so this is like how like people predict on human behavior. Ki, if they see the 10, 15 people and they find the trend of the people, how their behavior, the same way this algorithm works in that ki how the trend is there, and on that it decide. Yeah. So yes, Praveen, let's start your part.
Okay, sir.
So there was one question, Praveen, before that. So hopefully we are going to help in getting this open source software, installing.
Yeah,
Like,
yeah.
so
Yeah,
these
we'll have
things.
one session on that as well. Yeah.
Yeah, sure. Yeah. Thank you.
So this will be like a very brief go through on how to write a code. Okay. So as discussed, remember that we are solving the one-dimensional linear convection equation. Okay. So for that, I hope my screen is visible actually. Okay. So the size and fonting are clear. Okay. Right. Right.
Yeah,
So
it's visible.
yeah. Yeah. So what I was saying is, so we are solving the linear convection equation, and you remember that the discretized form of equation needs to be solved in, right? Okay. So that's the key thing in here, right? So what we have in here are we are importing a set of libraries, okay, for us to solve the equation. And first thing is we are actually considering 61 number of nodes. Okay, there is a reason for considering odd number of nodes, which I will discuss later on. And we will get the distance between the each node as 2 by nx minus 1. This is very common logic. Okay. Right. Once we get the dx, now what we will do is to initialize the number of time steps that we require. So this is just a user guess. So you can put in 20, 40, 60 or 80, something like that. And the more you put the time step, the more the wave will be likely to be get conducted. Okay. And we'll give the time step sizes for this. Again, this is also a user choice. Okay. So it varies depending on what value you are going to go ahead with. Okay. And we'll give the value of c, which is the wave propagation speed, as 1, and the value of u to be np dot. We initialize the u as an array which contains vectors of 1, right? And the value of u between 0.5 to 1. That's what I said, right? So between 0.5 and 1, you have a velocity of 2, and everywhere you have a velocity of 1. Okay? So that's what is being done in here, right? Okay. And we have the waveform, which if I plot in, it's how it is shown in here. Okay. So this is what you can see from this. Okay. Now, if you can see it doesn't look more like a stub. It looks more like a trapezoid. Again, I leave that thinking to you. You can just easily figure out why that reasoning is there. Okay. Okay. Fine. So once this is done, now we have to solve the equation. Remember, this was our equation, right? So u of n plus 1 is u of n minus c times dt by dx times un minus 1. Okay. So that's what is the key thing in here. Right? Okay. So once that is done, so we solve this, and once we get this, you can see the equation in here. Okay. So this is what is what we are trying to do this. And you can see initially the waveform was like this, and after some time, the waveform has moved in. And you can try to play around with the value of C, and as you increase C or play around with DT or anything, the value of gets stabilized, destabilized. Okay, which is what we'll study in the stability analysis. Okay, so hope that is understood for everyone. Okay, is it clear, guys? Any doubts you'd like to put forth? Anything? So this is again like I said, no, it's a very basic thing. So this is a very basic thing. So once anyway, this course actually requires you to not have any background on coding. So we'll start with the very basic of Python coding. And once we start with Python, we'll discuss in detail about how to go about and use certain libraries and install them. Again, fret not, we'll install all these sort of Jupyter notebooks and other tools that we require for the analysis. Okay, and also beforehand, so for the people who have registered, I would like you guys to download the ANSYS student version, which is available in their website. Okay, because it's a 20 GB file. Depending upon the network usage, it might take some time to download that. So please download it and keep it handy. Once the classes start on Sunday, we might. I'll just give you a walkthrough of the platform. Okay, so that's all from my side. And any doubts you want to ask me? Anything? See, this is. I am using VS Code for a lot of things, not just for Python, for C++ as well. Okay, so that's why I am, going with Jupyter Notebook. But if you want, you can also use any other tools of your choice. Okay, so that's why I'm saying. Okay, is it clear? Okay, guys. So if there are no doubts, then we can wrap up session.
Yeah, there is one doubt.
Okay.
Looking a bit scary.
Bit
Parthiv is
scary.
asking.
Well, it's not scary actually. What are they asking scary about? Is it the graph or the thing? What is that? Yeah, see, like I said, no, don't worry. Okay, that's a really the worry to me. Okay, see, this course actually will start with very basic. See, first 2 weeks we'll spend on the mathematics. Okay, I'll only touch coding once we are strong with mathematics. Okay, me and myself and Sanjay will take care of that, and Mr. Shivam also will pitch into, and we'll just take some portions of it. Okay, once that is done, only we'll jump into code. Again, we'll start with very basic of Python, printing hello world and hello IGC something like that. Okay, we'll start with that very basics, and once that is done, only we'll jump into coding. Okay, so don't have to worry about anything for now. Okay, right? It actually doesn't even look scary. It's just like a very basic code. Okay, once you learn the coding, you will also see that this code is actually a bit of a joke. Okay, this is a very basic code, and you don't even use this nowadays. Okay, but since for learning purposes, we have to have a basic standards or basic reference equations to code. Okay? And that's where this code comes in. Okay, right? So don't worry about that tough difficulty and all sort of stuff. Okay, leave that part to. That will be taken care of.
Okay, so I think Shivam's part will come late. Before that, they should understand the theoretical aspects of CFD as well as this coding part, then application part. So till that, Shivam will help them out in solving assignments and helping to understand these uh, theoretical aspects.
Yeah, sure, sir. I will. Till then, I will do that.
Yeah, sure. So, any other doubt, guys,
Anything which you want to ask? Any doubts?
regarding course? Because this is like the last demo. We had one internal demo class prior, and this is the open demo class. And then first class as planned, we will be having on Sunday. We can plan at 5 o'clock evening, right, Praveen?
Ah,
5 to
yes,
7 p.m. Yeah.
yes, yes, yes.
So I think that time IGC classes are not scheduled. So Sunday we will have 5 to 7, and Monday and Friday we'll have like this 8:50 to 10:50 or 9 to 11. So
Okay, sir.
any other doubt, guys? Guys, I want to tell all of you, Parthiv and other people. See, this is a different course from what you learn in GATE Aerospace Engineering or maybe in basic subjects, because here multiple things are involved. So it may take some time for you guys to get accustomed. Clear? Once you get accustomed, once you find interest, then it will become easy. Yeah, recording of the classes will be available, and it will be on IGC online platform only, Akhil. Okay, so I'll share all required tomorrow. Okay, and guys, don't worry, as we decided, recording will be there, but guys, do join live classes where you guys can interact and ask more questions. And of course, even for many people, gate courses are like gate subjects also tough, right? You know, Praveen and everyone, right? Gate is again, it's more about physics and mathematics only, right? Understanding of physical aspects and mathematical aspects. But CFD is next. You have to understand the computational aspects also, which is like coding, or if it is a commercial software, how to interpret results and all. So guys, uh, of course, this course is not an easy course, but we will try as best to make it as easy as possible. Yeah. So Sanjay, you can share your thought on this, because the what I have seen, people have shown much more interest in this course than even our regular gate course, right? Many people, even you can say, if you take IGC of 25 batch, when we did poll, Praveen, more people polled. Okay, then if we ask now, how is your gate preparation?
Hmm.
Then only some, maybe even 30, 40 people will respond. But for
Yes, yes, yes.
CFD course, we have seen more than 100 people responded. So that
Correct, correct.
means there is more fantasy for this course than gate preparation in actual, even for enrolled students, because
Ah, yeah.
of, the fanciness of CFD, like colorful pictures they see, right? But
Yeah, yeah, yeah.
Sir,
actually,
I would like to
uh,
add something here.
yeah, yes, Siva, please, Anna.
As Sir was saying, I was about to say that same point. Like CFD being so much like I showed you some colorful pictures and Praveen showed you code. This I'm talking to every student here. But to let's understand this first. Like colorful part is something which got you to learn about the CFD and enroll in this class. But again, if you want to be a good CFD engineer, first you need to understand what is the mathematics behind all that. Number one thing. That will take time to build up. Okay.
Yeah. So, guys, you need to have good patience, and if you want to work in future in aerodynamics and propulsion area, this CFD technique is very much required, very much useful, uh, and there is a good career future. And basically, CFD is not research. It is one of the technique which is used in research. You guys should be clear about that. If you know CFD means you have done some research. No, CFD is a kind of handful tool which you can utilize in many of your good research in the area of aerodynamics, propulsion, gas dynamics, and so on. Okay, so guys, just keep things in your mind. uh, this is one of the interesting course which we are starting at IGC, and many thanks to Mr. Praveen, for taking initial initiative, and then now Sanjay and Shivam is, you know, uh, making it more, interesting and impactful. Hopefully, once this course is done, and surely we'll miss Mr. Rahul. Initially, he committed, but now he has some more commitment, so he may not be directly part of this course. But as and when he is available, he will also share his insight. Uh, Rahul sir wanted to tell the basic difference between FEM and FVM and FDM. So we'll have one class sometime ki how these three different numerical methods works and where these are used. Specifically, FVM and FDM is used in, computational fluid dynamics part, and FEM is used mainly for structural analysis. So there he may give more input. So now Sanjay, you can share your last insight, and then we'll wind up.
So, just as Praveen and Shivam had mentioned, CFD is one such important course, and like Dinesh sir mentioned, it is not really research, but it is a tool that you need to do. You need to get into research. So, of course, you need the physical understanding and mathematical understanding behind these the software that you use, the results that you get. Only then it would be meaningful. But then you also need to understand how to use these tools in order to get those results and use them in your research. So yeah, it would be really interesting. I believe we'll add to more to this course, how much ever we can, and we'll make the best out of it. So yeah, that's all.
Yeah, thank you, Sanjay, thank you, Shivam and Praveen. So let's wind up, guys. If you have any query, quickly put in chat, and hopefully we'll solve as many query during classes. And of course, we also learn with you guys as journey begin from Sunday. Thank you, guys.
Thank you, guys.
Thank you.
Thank you, everyone.